Okay, you are welcome to day 2 of the training session on understanding the basics of centrifugal pumps from detail engineering perspective. So, if you can recall, in day 1, we were able to look at the classification type, identification of centrifugal pump as per API 610, and I made mention that API 610 is actually the international standard governing the basic design of centrifugal pump. So in continuation of this training session on understanding the basics of centrifugal pumps from detail engineering experience, we are going to move straight to what we have for today, and that is we are going to be starting from understanding what pump head is all about. Understanding what pump head is all about. Like I mentioned during the last session, I said that pump head is the maximum height that the pump can achieve pumping against gravity. I mentioned that imagine you're able to move the discharge line of your pump. Imagine you're able to move that discharge line of the pump. You move it straight up into the air with the pump in operation. What do you think will happen? As long as the pump is running, it will move the fluid to a certain height measured in meter. That height to which the pump can raise the water to is called the pump head. All right, and that head is expressed in meter. So if a pump can produce more pressure, it simply means that it can pump water higher and at the same time produce a higher head. So that is the concept of pump head. So that height to which your pump can raise the water to is referred to as the pump head. Now, there is a relationship between the pump head expressed in meter and your pressure. You are going to be seeing the relationship between that head in meter and the pressure in the course of this training session. So we move to understanding how how your suction tank levels varies with the pump head. What happens when the liquid level in your tank is low compared to when the liquid level in your tank, your suction tank in this case, is high? What happens when you have different levels of fluid, when you have different levels of liquid in your suction tank? How does it affect your pump head? How does it affect that height to which the pump can raise the water to, right? Which is called the pump head. Now, if you can look at this critically, you see for case 1, you see the suction tank level. If you look at for case 2, you see the liquid level in the suction tank for case 2. Now, if you look at case 3, you see the suction tank level in case 3. Now, what this is telling you is that as the suction tank level is increasing, the pump head is also doing what? Is increasing, right? As the suction tank level is reducing, your pump head is also reducing. So the height to which the pump can raise the water to is a function of what? Is a function of your suction tank level. So you see how the pump head varies with the suction tank level. The lower the suction tank level, the lower the pump head. The lower the suction tank level, the lower to which the pump can raise the water to, the lower the height to which the pump can raise the water to. Meanwhile, the higher the suction tank level, you see, the higher the height to which the pump can raise the water to. Now, so as you are, as the pump is put into operation, the suction tank level will be varying, right? Now, if as you are raising or lowering the suction level of the tank, as you are raising or lowering the suction level of the fluid in the tank at your suction, what you are doing is you are adjusting the what? The potential energy of the fluid available at the suction of the pump. So, meaning that if you lower with a lower or with a reduced suction level, this is very important, because by the time you are calculating your MPSHA calculations, you are doing your MPSHA calculations, you are going to take account of your suction tank level, because it directly affects the operations of your pump. So now what you are doing here is, as you are lowering the suction, as the suction level is being lowered, the potential energy available at the suction of your pump is also being lowered. Now, as you are raising the suction level, as the suction level of your pump is being increased, the potential energy of the fluid at the suction tank, at the pump suction, is also increasing. So you see how the pump head varies with the suction conditions. All right, that is very, very important for you to take note. Now, there is another. So we've looked at the pump head. I mentioned that height to which the pump can raise the water to is called the pump head. And I told you that as your suction tank level varies, right? It directly affects, the potential energy of the liquid available at the suction of the pump, at the pump suction. So there is another concept of head that you need to take account of, and that is called what? And that is called the total. That is called what? The total head. Pump's total head. Now, a much more useful of head as far as centrifugal pumping system is concerned is that difference between the liquid level in the suction tank. Don't forget, I said by the time your pump is being put into operations, your suction level will be varying, because there will be a constant flow of liquid to your suction tank. And if there is no constant flow of liquid in the suction tank, your suction tank level will be reducing. So there is always, increasing or lowering of your suction tank level as long as the pump is in operation. Now, with that in mind, I said a much more useful of the concept of head is that difference between the liquid level in the suction tank, that liquid level in the suction tank, and the head in the vertical discharge pipe. That difference is known as the total head that the pump can produce. Now, let me repeat this. The difference between the liquid level in your suction tank and that head you can see in this picture, that head in the vertical discharge pipe, that head in the vertical discharge pipe is what is denoted by this HD1. That is the head in the vertical discharge pipe, denoted as your what? HD1. The difference between that head in this vertical discharge pipe and the liquid level in your suction tank, that difference is known as the total head that the pump can produce at any given point. So now, increasing the level of the liquid in the suction tank will do what? We give rise to the increased head, like I mentioned. And at the same time, decreasing the level will give rise to what? To a lower head. So pump manufacturer, what they do, pump manufacturer and suppliers, often they won't tell you how much head a pump can produce, because they cannot predict what the height of the liquid in your suction tank will be. Instead, what the pump manufacturer or the supplier will give you is they will report the pump's total head. Very, very important for you to take note, because they cannot predict what the height of the liquid in your suction tank level will be. So they won't give you, they cannot tell you how much head a particular pump can produce. Instead, what they will report, it will be the pump's total head, which you see on your pump curve. And that is that difference in height between the level of the liquid in your suction tank, which is denoted as this HS1, the level of the liquid, okay, in the suction tank, and the height of a column of water that the pump can achieve. That is the total head. That is why you should always calculate. It's always advisable that you calculate the total head requirement, because it's a major requirement for you to select the right pump for any given application. So you should always calculate your total head requirement based with an assumption that your suction tank is empty, as that is when you will need the pump to produce the most energy, because at that point there is no enough potential energy available at your what? At your pump suction. So when you are calculating your total head requirement, it's always advised that, right, you always calculate the total head requirement based on a suction empty tank, as that is when you will need the pump to produce the most energy. So you will need your pump to produce, because there is no potential energy, there is no enough potential energy coming from the suction of the pump into the pump. All right, so the liquid is not giving any help in the form of potential energy when the tank is empty. So this is where most designers get it wrong. So your total head requirement should be based on a suction empty tank, as that is when you will need the pump to do what? To provide the most energy. At that level, the liquid will not be giving any assistance in form of potential energy when the tank is empty. All right, now that is the concept of the total head. So now we have defined the total head to be that difference between the level of the liquid in the suction tank and that height of a column of water that the pump can achieve. So if you look critically, your total head requirement is going to be your what? Your HD1, which is that height of a column of water that the pump can achieve, minus the level of the liquid in your suction tank. So it is always advised that, right, you calculate this total head requirement based on an assumption of a suction empty tank, so that you can have enough total head requirement that will enable the pump to work satisfactorily over period of time. That is very, very important. You will see it by the time you see the importance of this, by the time we are doing some calculations. Now, that's the concept of total head. Now, I also mentioned that, look at this, we now have different, pumping applications to determine your total head. we have a positive suction system. There is a positive suction system where you have your suction tank above the pump center line. Then you can also have your what? Like you have in this case. This is a positive suction system because your suction tank is just by the pump center line. So you can directly say that your total head is that the height is that height of the liquid at the discharge end of the pipe minus the suction tank level for a positive suction system. A positive suction system is that system where you have your suction tank just at or above the pump center line. Now we now have another application where, say in the case of well, a pump drawing liquid from a well or from a reservoir, that is a negative suction system. So if you are drawing, if your pump is drawing liquid, say from a reservoir, with the same pump where the level of the liquid is below the pump center line, like you have in this case, that is negative suction system, the pump will still produce the same total head, but the discharge head, this HD, will definitely go down. So this simply means you may not have enough pressure to run your devices, and you may need to consider getting a pump with a higher total head if you did not put into consideration the kind of pumping applications you are working on. So I put that to buy the correct pump, to get the correct pump for your applications, first you need to know what the total head you need and at what flow rate. So this is the beginning of any detail engineering activities as far as centrifugal pump is concerned. For you to be able to select the right pump for your applications, you first need to know how the total head requirement can be obtained and at what flow rate. Now, like I mentioned in the course of this training session, that your total head requirement is actually the difference between the height of the liquid, at the discharge end of the pipe, at the discharge end of the pump, minus the suction tank level. And this is for what? This is for a positive suction system. In the case of a negative suction system, that your total head will not be that difference. It's going to be a sum of that. You see, that height, the height from the pump center line to the liquid level, which will serve as your S. So it's going to be the sum of your HS and the liquid, the height of the liquid at your pump discharge end. That's going to be your total head requirement. You will see in the course of the training sessions, by the time we start some calculations, so that you can have a better understanding of what I'm trying to say. So in a nutshell, I put to buy the correct pump for your applications, the number one thing that you need to know is, how do I determine the total head requirements for these pumping applications? And I mentioned to you that in doing this, you have to first decide, are you having a positive suction system or you are having a negative suction system? Now, once you have determined the kind of suction system you have, I made mention to you that your total head requirement calculation should be based on a suction empty tank, as that is when you will need the pump to produce what? The most energy, because at that level, the liquid is not really giving much help in the form of potential energy when the tank is empty. All right, so that is that about the pump's total head. Now, another thing that you need to also be familiar with is your what? Is your frictional head loss. Frictional what? Frictional head loss. You see, one thing about pumping system is that when your pump is put into operation, you are either increasing the flow rate or you can be reducing the flow rate. Now, when you are increasing flow rates with the pump in operation, what do you think will be happening to the pumping systems, the overall pumping system? You are introducing friction into the system as the liquid is traveling along the pipes from the suction tank to the pump, and at the same time from the pump into the discharge pipe. You are introducing what? Friction with the increasing flow rates. Now, what do you think will happen with this friction? This friction reduces the amount of total head, don't forget, that the pump can produce. That friction that is introduced into your pumping system as a result of the increasing flow rate is going to have an adverse effect on your what? On your total head, because with the increase in friction, as the flow increases, the frictional forces, the friction in your pumping system increases. Same way, the total head will continue to be decreasing. So the amount of head or the amount of energy loss due to friction of the fluid moving through the pipes and fittings is referred to as the frictional head loss. I repeat, when you have an increased flow rate, what you are doing is you are introducing friction into the pumping system, and this friction will reduce the amount of that total head that you have calculated initially for the pumping applications. So the total head that pump can produce, imagine if you have made requirements or you have calculated your total head requirements to be HD minus HS, which is the height of the liquid, the difference between the height of the liquid in your discharge pipe and your suction tank level. Say it is 5 meters, for instance. With the introduction of the friction as a result of increased flow rates, that total head, all right, that total head capacity of the pump will reduce as a result of what? As a result of the friction introduced into the system. So the amount of head that is lost due to friction is called friction or friction loss or frictional head loss. That amount of energy loss, because you will lose energy with the introduction of what? Friction in your pumping system, because as the liquid is moving from one point to another, from the suction tank level to the discharge and to the downstream equipment, friction is being introduced into the system, and this will affect directly the overall performance of the pump. So by the time you are actually selecting pump for any given applications, you have to take into account the possible frictional head loss in that system. So in a system where there is flow, I told you the total head is that difference between the discharge head and the suction head. Now, with the frictional head being taken account of, your total head should now be that difference between the discharge head and the suction head plus the friction head. And so all this should, of course, must be less than your shut-off head. By the time we move into calculation, you will understand these concepts. You see, a lot of engineers find it so difficult to relate all these different types of head, with respect to pumping applications. But it is very, very simple. I started by mentioning what pump head is by saying that the pump head is that height to which the pump can raise the water to. And then I move to what total head is all about, which is that difference between, the height of the liquid, in your discharge pipe, that difference between the height of the liquid in the discharge pipe and your suction tank level. And if you recall, I mentioned that it is advisable that by the time you are calculating your total head requirement, you calculate it based on an assumption that your suction tank level is empty, because at that point there is no enough energy, there is no enough potential energy coming from your suction into the pump. All right, so you will need your pump to be able, with the right total head requirement calculation, your pump will be able to successfully operate without any adverse effect on the pump, with a very low reduced suction tank level. And at the same time, I mentioned that with an increased flow rate in your pumping system, there is also a terminology that you need to be very familiar with, and that is the frictional head loss. Because if you don't take account of your frictional head loss in your calculation by the time you are calculating the total head requirement, and you bring that pump and you install that pump, with a total head requirement calculations without taking account of the frictional head loss, by the time the pump is put into operation, and frictions starts manifesting in the pump, that total head capability of the pump will go down. All right, so now the question is, how do you determine, or how do you calculate what your frictional head loss? How do you determine the friction head loss for a given pumping application? Now, you see, determining frictional head loss, dynamic of frictional head is equal to the sum of the fittings head loss and the straight run head loss. It's as simple as that. So to determine your frictional head loss is going to be the sum of the fittings. You have fittings like elbows, you have fittings like T's, you have fittings like your reducer. Different types of fittings are both the suction and the discharge end of the pump. So the frictional head loss will be the sum of that fittings head loss and the straight run head loss. Excuse me. So the question now is, what is fittings head loss, or how is fittings head loss calculated? How can you determine the straight run head loss, so that the sum of these two can give you your frictional head loss? Because you are going to need it by the time you are calculating your total head requirements for the pump you are intending to purchase. Now, determining the fittings head loss. Don't forget, I mentioned that the frictional head loss is the sum of the fittings head loss and the straight run head loss. Now, taking fittings head loss first. The fittings head loss is expressed, or is calculated with this expression. The fittings head loss is calculated by what is known as K-value method. K-value method. Now, you have your fittings head loss denoted as HF being equal to your K V square over 2G, where the HF is the fittings head loss in meter water gauge. Your K is the total K value. Now, the question now is, how do you determine your K value? Each type of fittings, such as valves, bends, teeth, any kind of fittings you can think of, they have their characteristics resistance coefficient. or called K values. The K value is that characteristic resistance coefficient. So each fitting in your piping system for your pumping applications has their respective K value, which of course you can see these values in so many piping texts online. Now that is that. Your V is the velocity obtained from your Q equals to AV, and your G is the acceleration due to gravity. Now the question is, how do you determine your K, the K value, so that you can put that expression here to get your fittings head loss? I mentioned that each type of fittings has their respective characteristic resistance coefficient. E.g., the K value for say 45-degree elbow is around 0.4. For 90-degree elbow is 1. The K value for 90-degree elbow is 1. Then some valves, the K value is I think 0.7. So now, to get fittings head loss with this expression, to use this method, what you need to do is, to get your K value, you need to count the number of fittings, the number of valves on the P&ID, the number of fittings such as your bends, your tees on the P&ID. The P&ID is the piping and instrumentation diagram. So when you count these items one after the other for the relevant suction or delivery line, so let's say for a given pumping applications you have 10 bends, 4 tees, 3 valves, you have this. What you need to do next will be to multiply the number of each type of fitting by the corresponding K value. So if you have 4 45-degree elbow, don't forget each K value of 45-degree elbow I said is 0.4. So all you need to do is you take the K value of one 45-degree elbow, which is 0.4, multiply it by 4. If you have 4 45-degree elbow, if you have say 3 90-degree elbow with a K value of 1, you will say 1 multiplied by 3. Alright, so you multiply the number of each type of fitting by the corresponding K value. After you've gotten all the numbers, let's say you have 5 valves. What is the K value of each of the valves? Multiply it by the number of the valves you see on the relevant suction or delivery line of the pumping system. So the next action will be to add the K values for the various types of fittings together so that you can obtain what? The total K values. So you put it in this expression. And of course, with your superficial velocity, which is your Q equals to AV, your Q is your flow rate, of course the area of the piping, then you can get your velocity. Your G is your acceleration due to gravity. When you put those values here, you have what you call your fittings head loss. Don't forget, what we want to calculate is the frictional head loss. The frictional head loss is the sum of the fittings head loss. That sum of what? The sum of the fittings head loss and the straight run head loss. Okay, so what we are looking at currently is how to determine the fittings head loss. And I said the fittings head loss will be determined with what? The K value method. I've explained this. So the next thing will now be, how do you get your straight run head loss? Your straight run head loss can be obtained from the Darcy-Weisbach equation, which of course states that for a pipe of uniform diameter D, the pressure loss due to viscous effect delta P is proportional to the length and can be characterized by this expression. The Darcy-Weisbach equation, if you can recall, states that for a pipe of uniform diameter d, the pressure loss due to that the viscous effect is proportional to length L and can be characterized by this expression. So here your delta P is the pressure loss. All right, your L is the length of the pipe. Your FD, according to the Darcy-Weisbach equation, is the friction factor. And if you can recall, the friction factor is dependent on the Reynolds number. For you to get your friction factor is dependent on what? On Reynolds number. And Reynolds number is nothing but that expression which is directly proportional to your density of the fluid, your fluid velocity, and the internal pipe diameter. And at the same time, it is inversely proportional to what? Your fluid dynamic viscosity, as you can see in this expression. Now, of course, this is your density. Now you have your fluid velocity and you have your D, which is the pipe internal diameter. So with this expression, you can obtain your what? Your straight run head loss in form of the pressure loss. And recall that I said in this expression, your FD is the friction factor and is dependent on what? Is dependent on Reynolds number. All right, so let's look at this. Now, we now have different fluids with different Reynolds number. Now, if you calculate your Reynolds number with this expression of Reynolds number, the density, what is the density of your fluid? What is the velocity, the fluid velocity? What is your internal pipe diameter? All right, and what is your fluid dynamic viscosity? Now, when you put that values together to obtain your Reynolds number, if your Reynolds number for fluids with Reynolds number of less than 2000, we know that the flow behavior is what? Is considered to be a stable laminar fluid flow. All right, now so for a stable laminar fluid flow with a Reynolds number of less than 2000, your friction factor, which you need to obtain first before inserting the value into the Darcy-Weisbach equation to obtain your pressure loss due to viscous effect, which is your straight run head loss. Okay, so your friction factor will be 64, will be equals to 64 over your Reynolds number. This expression for friction factor is for a stable laminar fluid flow, that is the fluid flow with Reynolds number of less than 2000. So if your Reynolds number is less than 2000, just get your friction factor with this expression and put the value into this Darcy-Weisbach equation with your length of the pipe. Now the friction factor FD that you have obtained, the density of the fluid velocity, and the pipe internal diameter, you can obtain your what? The pressure loss due to viscous effect in terms of delta P, which will be your what? Your straight run head loss. Now, another thing is, if you now have Reynolds number, say greater than 4000, the fluid, of course, is considered turbulent. Is considered what? Is considered turbulent. So to get your friction factor FD, which has to be inserted into the Darcy-Weisbach equation, please take notes. You are going to make use of this expression. Colebrook-White approximation will be used to estimate the Darcy friction factor from Reynolds number greater than 4000. So you see this expression, I know you must have seen this expression in different texts. So the Colebrook-White approximation will be used to estimate your what? The Darcy friction factor for a turbulent flow, that is with a Reynolds number greater than 4,000, this expression will be used to obtain your friction factor, which we have to be put into what? Into Darcy-Weisbach equation to get your straight run head loss. Are you with me? So now, of course, if you look at this expression, your FD is your friction factor, which we are looking at. Your DH here is the hydraulic diameter of the pipe. What is the hydraulic diameter of the pipe? You put the values there. Then your E is the surface roughness of the pipe. Depending on the material, the type of materials for the pipe, you are going to have the E, the surface roughness of the pipe. All right. Then with the Reynolds number that you have calculated, you put this together in this Colebrook-White approximation to obtain your friction factor, which is the FD. Now, with your FD, you come here, you put your FD for a turbulent flow, right? Obtained from the Colebrook-White approximation. So to obtain your what? Your pressure loss due to viscous effect, which in this case is the straight run head loss. All right. So what you have will be your, of course, your straight run head loss. Now, you can now ask me, what of for Reynolds number between, say, 2,000 and 4,000? Such kind of fluid are considered unstable and can exhibit either laminar or what? Can exhibit either laminar or turbulent behavior. So this region is normally or is commonly referred to as the critical zone, and the friction factor can be difficult to predict. Take note of this. This is very, very important. For a Reynolds number, say by the time you put your fluid characteristics to get your Reynolds number, we say for Reynolds number, say less than 2,000, you can use FD equals your 64 over your Reynolds number. And same way, if your Reynolds number is greater than 4,000, we say is turbulent flow, then you can use the Colebrook-White approximation to first obtain your friction factor. But the question now is, what if the Reynolds number is between 2,000 and 4,000? We say such kind of flow is unstable and so can exhibit either laminar or turbulent behavior. So this region is, of course, for the friction factor calculation, it can be very difficult to predict. So judgment should be used if accurate predictions of fluid loss are required in this region. So I put it simply that you can use either equation 1 or 2 for this critical zone. You can use either equation 1. So this is going to be your judgment as a designer. This is going to be your judgment as a machinery engineer to determine which one to go for. If you have for fluids with Reynolds number in between 2,000 and 4,000, because the flow can exhibit either laminar or turbulent behavior at any given point. So judgment should be used if accurate prediction. So this is where experience comes into place, because you can actually use either one of the two. So that is how you obtain your what? Your straight run head loss. So with your fittings head loss and your straight run head loss, you can add the two together to get your frictional head loss. Is that okay? Now, with your frictional head loss calculation in place, with your total head in place, adding together the static head, the fittings head loss, and the straight run head loss will give the what? The total head the pump needs to generate to overcome resistance and deliver the specified flow rates to the system. So adding together your static head and your what? Your frictional head loss. Your static head in this case is going to be that difference between the height of the liquid in your the height to which the pump can raise the water to at the discharge end of the pump, and the liquid level, the suction tank level. That difference is going to be your static head. So adding together the static head and the fittings head loss with the straight run head loss, in which the two of them is just what? Is just the frictional head loss. It will give you the total head the pump needs to generate to overcome resistance and deliver the specified flow rate to the system. So you can see how important the total head requirement calculation is by the time you are doing detailed engineering of your pumping system. By the time you are making some critical decisions, right, with regard to your pumping application system. So you need to take note of this calculation. So your total head requirement will be that which the pump needs to generate, that head the pump needs to generate to overcome any form of resistance, and at the same time be able to deliver that specified flow rate to the system. You don't want to be the engineer responsible for installing a pump which is not capable to deliver a required flow rate at a given head or pressure. This is the beginning of the problem. So you don't want to be the engineer responsible for that. So that is why you need to critically look at the overall design of both your piping systems and, of course, what you have available on the site, so that you can know, okay, to which height in which the discharge tank is placed. What are the fittings available in both the suction and discharge piping arrangement? Because you need to determine the frictional head loss in that system, as that will affect your total head requirements. If you don't put that into consideration before you finally select a pump for any given application. So these are the concept of head that you need to get familiar with in order to confidently select pump for any given process application. So for today's session, we have looked at the pump head. We have looked at how the suction tank level varies with that height to which the liquid, right, to which the liquid can raise the water to, how the suction conditions affect the overall operations of the pump. We have looked at what total head requirement calculation is all about. We have looked at how the frictional head loss and the effects frictional head loss will possibly or will most likely have on your pumping system if you don't take note of it during your detailed calculations. So for today's session, because I don't want us to rush too much, I'm going to end for today. So tomorrow we are going to continue on understanding the basics of centrifugal pumps from detailed engineering perspective. So for those that are yet to subscribe to the channel, please do well to subscribe and press the bell button so that you can always get notification by the time I put some of the video sessions, right? Some of the video sessions that I will be uploading or that are uploaded, you know, from time to time, that I'll be uploading from time to time as well. Different equipment. We are on pump series. We are still going to talk about compressors, steam turbines, gas turbines, and at the same time, mechanical designs of various static equipment. So for you to get more information, for you to always be notified whenever I put such videos on this channel, please do well by subscribing to the channel, and at the same time like some of our videos and share on your professional networks. You can share on LinkedIn, you can share on different professional networks with your colleagues at work, because my motive is to ensure that this information is readily available to all engineers. All right, so thank you very much. Thank you for your time. See you in next session. Bye.